Good afternoon. Welcome to lectures 91 and 92 on thermodynamics of materials. We will continue with solution thermodynamics. Today we will actually do the integration of this equation. Activity coefficient versus temperature relationship, this equation number 2, will do the integration, and so these are not required anymore. So just we will actually integrate between temperature T1 and temperature T2. These are all discussed last day, so no point. Right. Just I will rewrite this equation on the top. To begin with, this is the activity coefficient temperature relationship. That's nice. Now it is actually now fit. So let me write this. Just copy this rather. D ln gamma I over dt del T rather constant pressure and composition pressure and composition is what? Minus hi bar m hi bar m over RT square. This was our equation 2. Today we will do the integrating. We will write this in the integrated form. This is the job on hand. Just the integrated form. This is differential form, integrated form. Integrating between temperatures T1 and T2. What we have? Del ln gamma I is minus hi bar m by r t square del t. Now integrate between temperature T1 to T2 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 and this corresponding gamma T1, this is gamma T2, or ln gamma at temperature T2, gamma at temperature, shall I write at gamma this way, gamma T1, it is better, no? If I gamma T1, this is better, gamma T2. So what we get? Ln gamma T2 by gamma T1 is what it is. R is constant, will be outside. Hi bar m will be considered constant. This I will explain. So if I take this out, I have hi bar m by r. Dt over t square is minus 1 by t. So 1 by, you check this, 1 by T2 minus 1 by T1. We consider R is a constant, easy, come out. Hi bar is considered constant, means independent of temperature. Is considered independent of temperature of temperature following the regular solution model that we'll discuss shortly. Following the regular model, following the regular solution model, regular solution model to discuss shortly, to discuss later. To be discussed later. So this is the, you can give a box to this. This is our equation, what? Call it 3. So we actually have this equation. Let me verify. Okay, T2 minus 1 by T1. Okay. So remove this. So equation 3 allows us to determine gamma activity coefficient, maybe am I right? Determine the activity coefficient at any one temperature when the activity coefficient at another temperature is known. And of course, what? Hi bar m is known. Okay, Hi bar m, the partial molar enthalpy of mixing, is known. So if we know gamma, I should have written here gamma I. I'm writing here gamma I T2. So gamma A or gamma B. So if we know gamma for one temperature, then another temperature we can find out using this equation 3. And provided Hi bar m is also given. So this is this. Please look at this and you see this equation 3 is, recall, this is similar to equilibrium constant temperature relationship. Equation 3 is similar to equilibrium constant, thermodynamic equilibrium constant K, temperature T relation. What was that? Recall this, ln K T2 by K T1 is what? Minus delta H0 by R 1 by T1 minus 1 by T2. So this is actually that we already studied. So today we found this, there is a similarity. We will actually use this equation in our assignment problems. So this part is over. So I will actually now go to the next. This was the remaining part of last day's class. That is effect of temperature on activity coefficient. So that is this is the concluding part. We have completed this. So we will now move on to the next topic. What is this? Shall I remove this? Let me write the topic. This topic is actually partial molar free energy and integral molar free energy. This. So to find, so let us write this. Okay. To find is the next topic. Next. To find next topic. See, it is under solution thermodynamics. Okay, next. To find what is this? Partial molar properties. Not necessarily free energy, it can be entropy, it can be enthalpy. Partial molar properties from the integral molar property, molar property in a binary system. In a binary system or binary solution, solution system we are discussing. So binary solution or binary system A, B. This is the topic. Start. We have already found, we have already discussed and it is easy to find the integral molar properties from the partial. A number of times we have done this. It is easy to find the integral molar property, the opposite of this, integral molar property from the partial molar properties, from the partial molar properties. How we have seen? Actually, let me remove all this. This is all over. So no need of this anymore. So what is example? For example, EG you can write what? G, say G. G is what? X A G A bar plus X B G B bar. G is X A G A bar. Delta G M or short, or in short G M, because M for mixing means there is a change. So delta X A G A bar M plus X B G B bar M. So these G A bar and G B bar are partial molar property. Partial molar property. What is the name to this? Partial molar free energy. Only partial molar free energy of A. No mixing. Just mixing is here. So these are also sorry. These and these also partial molar. Likewise, partial molar properties. What is the name? Partial molar free energy of mixing of A, and this is for B. What is this? This is this and this or what? This side is integral molar. So integral molar property. So this is integral molar property. This is integral molar property. There can be others also. Delta G excess or short G excess is what? XA GA bar excess plus XB GB bar excess. You know this number of times you have done this. So integral can be found out if partials are known. So similarly for others also delta G excess, delta HM maybe enthalpy, change the function enthalpy, or is in short HM what? XA HA bar M plus XB HB bar M. Delta HM, what is this? Another is entropy excess, say for example. This is also integral molar property, right, left hand side, all are integral molar property. Okay, delta S excess or simply S excess is what? XA SA bar excess plus XB SB bar excess. So these are the things actually. This is this we have. However, but today we are interested to know the partial from integral. It is from integral the partial. I'm sorry, from the partial we are getting integral. But today we will see from partial we are getting integral easy. From integral to partial molar from integral the partials. That is a little bit challenging. So, however, it is not so straightforward to find the partial molar properties. Partial molar properties from the integral molar property, from the integral molar properties, from the corresponding integral molar property. It is not easy to demonstrate this. To demonstrate this, to demonstrate this, to demonstrate this, to let us choose Z as the. Let us choose Z as the state function property. State function property, or say state function property as a state function, as a state property. Z as the state function or state property. State function or state property. Then we can write what? Z as the I have to introduce here as the integral. Acha, and we are considering binary system, na? What is in a binary solution, in a binary system, I've already given here AB. Okay, yeah. Just don't have to consider this already. So this is so let us choose this as the integral. So how can we write? Follow this rule. Follow this rule. If z is, then what you can write? X a z a bar, x a z a bar plus x b z b bar, z b bar. Then what you get? Dz. Dz is what? Differentiating. Differentiating. Dz is what? Tell me. X a dz a bar plus x b dz b bar plus z a bar dx a plus z b bar dxp. Now this is 0. This is 0 after Gibbs 2m equation. After the Gibbs 2m equation. Equation to be started shortly. To be started shortly. So what is left here is z a bar dxa plus zb bar dxb is what? Z a bar dxa, z a bar minus zb bar dxa. Why this? Because since xa plus xb is 1, a number of times we will use this. Hence, dxb is minus dxa. So, so you get this. Call this, will you call this a equation? Perhaps you give an equation to this. So you do one thing, z is dz is this, okay, or dz by, or continue this, or dz by dxa. So what? Z a bar minus zb bar. Acha, let us do one thing here. Actually, let us call this equation 1. Acha. Now, or you multiply by xb, xb dz by dxa is xb z a bar minus xb zb bar. Call it equation 2. So 1 and 2 by 1 plus 2 will get z plus dz dxa. Oh, this is 2. This is 2. Z plus xb dz dxa. xb dz dxa is what? If we add this on the right hand side, minus this term and this term plus minus cancel out, remaining z bar common xa plus xp, which is 1. So z bar. So we have, you can write finally. So we have z bar is z plus xb dz dxa. Box this. Shall I give a name to this? Call it equation 3 perhaps for reference. This is for A. Similarly, for B, ZB bar is Z plus XA dz by dxb. Equation 4. Enough. So this is the relation that we have to derive. This is we are looking for ZA bar, partial molar value from integral Z, and this side is Z as a function of XA or XB. So that I will utilize. Then we'll get, so it is about Z. Right hand side about Z, we get ZA bar, and when ZB bar, similarly we have the relationship, and again the right hand side is Z. Okay. So just note that ZA bar, this is very easy, dz by dx. Remember this, ZA, when Z. And ZB bar, dz by dxb. And if it is dxa, then it is xb. When it is dxb, it is xa. Easy to remember. And Z common in each case. So not very difficult to remember, or first you try to derive yourself. So what I shall do now, okay. Now I will show you that this is the analytical relation, okay, mathematical relation. So I will show you now the tangential intercept method. Tangential intercept method to find the same, to find partial molar property from integral molar property. So just this will be interesting. We will actually use, this is frequently used and particularly used in free energy composition diagram. This principle, tangent or common tangent, like this. So follow this. We will gradually proceed towards that, and we will finally pick up this free energy composition diagram subsequently. And where we will use this tangential. So what is the rule? Let me write tangential. Next, about this. What I do here will be consistent with this. Otherwise, it will be rejected. Whatever I do, tangential intercept method to find the partial molar, same objective, same partial molar property, partial molar property from the integral molar property, molar property, integral molar property versus composition plot, versus composition plot, consistent with equations what and what, 3 and 4. Let us say this will be consistent with this. Okay, 3 and 4. So suppose z is the chosen state function Z is the chosen state function and Z versus composition and Z versus composition, which is XB binary system. Z versus composition relation is known. Relation is known and given in the form of a plot. And given in the form of a plot. Figure 1. Figure 1. I will draw you this thing, figure 1, in the form of a plot, figure 1. Achha. Let me draw this. This is Z, the property. It may be G, it may be S, it may be H versus XB, the composition in the binary moving from 0 to 1. Call it A, pure B, as we do always. And let me give you the sketch. Suppose this is the Z versus XB plot. It is in maybe a relation that can be plotted, and this Z versus XB plot, and we are interested at a point C. And give some names other. Suppose this point, this is the component A, component B, but in addition I give some name A. This point is A, and that point is B. It will be helpful. And C is a chosen point at which we will try to find the partial molar property. So C is the chosen point. Okay, let me write now. Okay, C is the this is okay. This. So let me. Achha. C is a so C is a point whose coordinate is Z XP. So C coordinate is wait a bit. Actually, let me what I shall do. I'll draw a tangent here. Let us do this right now. Tangent hitting. Tangent should be still. Yes, this is the tangent at point C. What is the coordinate of C? C is Z. I've written here Z XB. Z XB. So C is a point. That means any point. C. It can be here. It can be here. Can be here. Can be there. Anywhere. Anywhere we can find the partial molar property from the integrated value Z XB. C is a point Z XB. Okay. C is a point Z XB on the curve. On the curve. On the curve. At the composition, C has the composition XB at the composition Xb means this composition, Xb. At the composition Xb, so for each composition we can get the partial molar values are partial values, namely Za bar and Zb bar are to be found. Okay, this is the procedure. Draw a tangent. This tangent at C on the curve. Tangent to the curve. Tangent to the curve at point C. At point C. The intercepts on the XB is 0 axis. Remember, XB is 0 axis is what? XB is 0 axis. Intercept on the XB is 0 axis gives Za bar. That is. So this is the XB is 0 axis, Y axis, but XB is 0. This is another parallel. This is also XB Y axis, but XB is 1 axis. So this is XB is 1 axis. This is XB is 0 axis. So tangent, draw the tangent at the desired point means composition. At the desired composition. So don't say point, composition. At this composition we are interested to find when the integral value is Z. This is the integral molar finite. I will write somewhere. This is the chosen state. Okay, wait a bit. The intercept on the y axis, this is Z bar. This is Z bar. This is our objective, and the other side is ZB bar. So gives Z bar, and the intercept on the XB is 1 axis gives ZB bar. So this is the tangential method. So draw the curve. Okay, fine. Now here I should mention here somewhere. Okay, okay. So Z is the chosen state function, and Z versus composition. You write. Z is the integral molar value. Shall I write? Relation is known, and Z you write, but you please add here. Z is the integral. Is it? Z is the integral. Is integral. Partial integral. Z is the integral molar value. Z integral molar value means molar property, whatever property. I have said Z, it can be enthalpy, entropy, free energy, internal energy, integral molar property. But remember, this is the integral. Z is the integral. And what will be the partial? Z bar and ZB bar. How to get this? Draw a tangent at the chosen point, at the point of interest, at the composition of interest. What is the composition? So this composition. If it could be like this, say, I'm not sketching here. I'm just showing actually, just dabbling here, like this. Suppose this point, draw a tangent, draw a tangent. This tangent will come here and hit here. This is the Z bar, and this side hit there, ZB bar. You want to draw here similarly, draw here. This is the tangent, hits here, ZB bar, hits here, ZB bar. So we consider this, but we say this is, now you might ask me, what is the rationale behind this? You draw a tangent and give the intercept. These intercepts are Z bar and Z bar. So we need some proof. Proof is what? You have to show through this diagram that Z bar comes out to be this, consistent with this and consistent with this ZB bar. So proof. So what is proof? Z bar. So let us say Z bar turns out to be what? But before this, I have to give some names. First of all, let me draw a dotted line now. These are construction line, dotted, and here also another dotted. Let me give this name C D, as I have used this. This is the D. This point is E. And this point is M. I think we will not mind the point M where it is. That value is Z bar. Z bar is here, and this will be obviously N. If it is N, and you write ZB bar. This value, this point is N. Here it is the ZB bar and M Z bar. This is the answer. What is the answer? What is the Z bar? This much. What is the ZB bar? This much. What is the Z integral? Z. This is the Z C point. XB composition Z. The whole diagram is Z versus XB. So each point is ZXB, ZXB, ZXB. So prove Z bar. Let us go on proving. Z bar is what? As you see in the diagram, AM is what? You see from this diagram is ED. ED is what? It is actually C, this point is C, remember. CD minus CE. CD is what? CD is, see the coordinate. This is Z. Z axis Z minus C. C actually little bit of rough work here. Achha, call this theta, angle theta. Theta, I write here since I cannot write inside. This angle is theta. Theta is the, tan theta is the slope. Remember. So tan theta, if I may write, tan theta, you follow this. Let's see from this figure. Tan theta is perpendicular by base. Perpendicular is C by ME. C, I am interested to find C. Let us see. C by ME. ME is incidentally same as AD. This is 0, remember. This is 0. This is not O. 0. AD. Sorry. AD. C by AD. C is what? C by ME is AD. Okay, very good. AD is very good. C. C is what? CD minus. Oh, that have I done this? Oh, this is already C. So C is what? AD is how much? AD is, tell me what is AD? Take a look. AD. This is XB coordinate. XB coordinate. This is the coordinate is XB. So AD is XB. Tan theta is so called M. Is what? Slope. Tan theta is the slope. Y is mx plus c. Straight line equation. M is tan theta. Tan theta is what? Here slope is derivative. The derivative. What is this? Tan theta is dz dy dx. Tan theta is dy dx. So dz by dxp. So what is c? Or c is what? We write xb times dz by dxb. Will you substitute this here? C here minus xb dz by dxb. You remember dxb is always minus dxa. I have written here always whole. Dxa is minus dxb. Dxb is minus dxa. Xa plus xb is 1 means dxa plus dxb is 0. Xa plus xb is always 1. Mole fraction sum to 1. So dxa plus dxb is 0. Hence you have this. So this minus dxb I am writing as plus z plus. I am writing is dxa. Then this minus and minus absorb dz by dxa. Actually, this is the result. This result is same as this. So we have proved. That means this is correct approach. It is consistent with this thermodynamic relationship. So I am writing here. So ZA bar. So ZA bar is, I am summarizing here. Z plus XB dz dxa proved. Proved. Next, ZB bar. You have to see ZB bar. Shall I remove this? Remove this on the last line. I will not remove. This is enough space for ZB bar. The last one, actually I have kept this. Let's prove ZB bar. Take up. What is ZB bar? Tell me. What is ZB bar? What is ZB bar? Start here. ZB bar. Now, next. ZB bar, according to our method, this tangential intercept on the xb is 1 axis means this y axis. Xb is 1 axis means this y axis. Parallel 2 y axis. Parallel. This is xb is 0 axis. This is xb is 1 axis. So what is the intercept? Here. Bn. Now split it into 2. Okay, again similarly you do this, please. Here, from here actually. Dotted line will do. Give a name to this. One name I have given, Bn P, maybe P. Straight line. P. What is Bn then? Again you should note this. If this is theta, this is the, okay, this angle is also theta, no doubt. So Bn, first break, Bn as Bp plus Pn. So now Bp is what? Bp is nothing but CD plus Pn. What is Pn? See, apply tan theta. So it was little bit where? Little bit here. Underneath somewhere here. Tan theta. Do this. Tan theta is what you see? Tell me. Pn by, the required is Pn by over base. Cp. Cp is what? Pn is what? Pn is, okay, wait a bit. Pn is what? Cp is what? Please tell me. Cp is actually dB. Cp is dB. dB is what? AB minus AD. AB minus AD. Or Pn by AB is what? How much is the AB? 0 to 1 means 1. AD is what? A moment ago, AD is what? XB. I wrote this. AD is XB. AD is XB. Okay. Here, AD is XB. See? AD is XB. AD, yes. This is x-axis. This is the measure AD, and the coordinate is also XB. Yes, C means AD is XB. So CD is what? I digressed. Oh, I'm talking where? Here. AB is 1 minus AD is what? XB. That means 1 minus XB is what? Pn by XA. Or, and tan theta as before, the slope is the gradient, is the derivative, is what? dz by, this is z versus xb plot, dz by dxb. Or what you get? Pn as right here, or Pn is xa times dz by dxb. Pn is xa times where you are Pn is xa times dz by dxb. So I substitute this here. Cd is what? Cd, tell me. Cd is what? Cd is the z. Cd is again as before. Cd is the z. CD is the z. CD is the z pivot. CD, yes, CD is the C coordinate of C is z. Z plus Pn is xa dz over dxb, or you can write this. So you are getting this here. You just write this directly. Zb bar is z plus xa dz by dxp. So we are very satisfied. Very satisfied, Sajal. Zb bar is z plus xa dz by dxp. Proved. This is analytical. This is the graphical. And this we use in the free energy composition diagram. Why you draw common tangent? Sometimes say common tangent. A tangent principle, tangent concept is here to get the partial value from the integral value. And at equilibrium partial values, Ga bar is Gb bar, Ga bar in the alpha phase is Ga bar in the beta phase. You know, common tangent, common. It is only one phase, liquid phase. Say. There are two phases will be there. So that's why common. Today is tangent, and that time it will be common tangent covering two phases, and each case intercept will give you the partial molar energy. Since common, the same value of partial molar energy, which is the requirement of equilibrium, and phase diagram is equilibrium diagram. So I will discuss this at length. Free energy composition diagram at length, but this is the background. Why we draw tangent? Given a curve, why you draw tangents? Okay, very good. So if you if you are giving z as a function of x, xb, etc., you analytically find out this. But take the differentiation and place this here, get z bar. No problem. No problem. Okay. But this gives us some insight into the free energy composition diagram. So this is all over. So now remove this. We will actually move into the next topic. Next topic is, interestingly, I tell you what, last day I was discussing that why the subject of thermodynamics is difficult to the students. Remember, I started this thing and I tried to explain this, but last day my class was not very clear. Okay, I actually very fast went through and not tidily presented, I should say. So I hope, actually I should be very tidy and point by point I have to explain this. So that I will take up, I want to finish that part. Why the subject of thermodynamics is difficult to understand for the students. Okay. So I'll give you the reasons. I told you other day, 3 reasons or 4 reasons later. So that 4 issues. So this is the topic. Next. Totally different. This different. I tell you what. This I will just in passing I discuss this in passing because this is my own opinion. So, but in passing I will discuss this. So it will help you to find the okay difficulty and to find the reason behind the difficulty, cause of the difficulty, and to remove the difficulty if possible. And maybe you have fewer pitfalls. So, if you are aware of this and you are okay, careful about this, that's why. So it is actually kind of little bit of digression from this mixed solution thermodynamics. This is not solution thermodynamics. So I remove this thing for the time being. For the time being, I am removing this. I will return to solution thermodynamics with the Gibbs-Duhem equation, next issue. And then integration of Gibbs-Duhem equation. This is, I will resume solution thermodynamics. Today little bit digression, but okay. So this is what I want to tell you. Sorry. So this is the one. A bit of digression from solution thermodynamics to cover some important, to note some important issues to cover maybe better, to cover some important issues in passing. We will resume solution thermodynamics after these issues are discussed. Explained. So this is important. So what is the topic now? Let us give the topic. This the topic is, let me write this topic is four issues four issues that make thermodynamics a difficult subject. A difficult subject to the students. I will first name these four issues. I gave the names last class, but okay, let us start fresh today, and let us have a tidy discussion. Okay, very comprehensive discussion. First, four. One, this is the trouble. This is the trouble. So I am giving you trouble. Why you don't understand thermodynamics? Use of D. D is the differential operator. D. In thermodynamics, you have seen number of times it comes. Okay, frequently comes. Every moment it comes. Reversible process you have come across. This process is sometimes we can't seem to follow reversible process. Maybe another difficulty. Third is presence of constraints. Presence of constraints. Constraints in thermodynamic relations. In thermodynamic relations. See, it is example constants. Remember this dgpt less than 0. These constants. These constants, or DATV less than 0 or DHSP less than 0, constants. Or again, see, in Maxwell relation, you have dG is VdP minus SdT. What is the constant? How do you write Maxwell? Maxwell, how do you write? Del V by del T, del V by del T at constant pressure is minus del S by del P at constant temperature. I write this little bigger font. Del V by del T at constant pressure. So always you see constant. Sometimes some people avoid the constants or don't consider the importance of the constant. Okay, so these are the constant example of constants. So these are these. So this will be covered here. How we are actually mixing up with these constants and we mishandling this constant or ignore. Ignore unfairly these constants. This is third. Fourth is what then? Fourth is concept of equilibrium. I tell you what, concept of equilibrium, you may be thinking that it is very easy, and when it was asked, many a time this answer comes, well, equilibrium state is when the forward reaction rate is backward reaction rate. Actually, this is a kinetic statement. Reaction rate is kinetics. So it is no thermodynamic statement. Thermodynamic we know, also even when we give the right answer that free energy is minimized. Under certain conditions, free energy of the system is minimized at equilibrium, or delta G is 0, etc., etc. Even so, but this is not. We may have to handle number of reactions, multiple phase, multiple component, multiple phase reactions, multiple reactions. But then what is this? DG of the minimum. So which one we consider? There can be multiple equilibria. So this I will discuss. We'll discuss today. Perhaps I cannot get beyond the first one. If time permits, I will take up the next one. Use of D. You just follow with me the difficulty. Cons A. These are all okay. These are the four. You draw a line. Now concentrate on this one. Okay, four issues. Okay, these are all you can remove this. Okay, later on, depending upon space required. Consider. Just follow me. Why the problem coming? Consider. I had problems. I admit. I admit that yes, I had problems with D. The D actually I wanted to penetrate into this. D, when D is used and how it is used, etc. So D, and I found that any time it was used actually just mechanically, like ritual. So we could not follow. Sometimes they are using, sometimes not using, sometimes going to delta. The confusion. Whether it is reversible process or it is a different irreversible process, you are using D. What? Let us see. You'll follow easily. Follow me. Consider H is U plus PP. You know this relation. Now get a differential of this. DH is what? You can write DU plus PdV plus VdP. This everyone can write. We write this. All the time we should consider why you are writing this. Why we are required to write this? What we will do? Most of the times, what we will do, we will integrate this under certain condition. So then integrated form will be useful maybe for the finite changes, because we will deal with the problem finite changes. So anyway, but this is a starting point. Don't jump into integrated form without writing the differential form. Write differential form, then integrate. This is required. Don't jump into the integrated form. Then you will run into errors. So this is correct. I would say this is correct. Correct statement. No harm. We know this. This du pv dpv means differentiation by parts pdp plus bdp is perfectly mathematical. But delta h is delta u plus p delta v plus v delta p is incorrect. This is incorrect. This is used in some widely circulated textbook. Incorrect. Why this? See, you the first line is correct. That is correct. Then you integrate this wrong integration. Wrong integration of dh. dh. Let's start. You start integrating. dh integration is delta h. 1 to 2 means h2 minus h1 is delta h. So next, likewise, du is delta u. Correct. pdb, how do you write p delta v? How you are entitled to write p delta v? Yes, you are entitled if it is a constant pressure process. Otherwise, you have to keep writing is integration pdb. You have to retain. You have to retain this 1 to 2. 1 to 2. How the moment you say it is outside means constant pressure, you have consider. If it is constant pressure, then VDP is where 0 dp. Constant pressure process, this term drops off, drops out. Okay, so you get this. So this is there is an existence of this term, but this is little b delta p. So this is the reason. So I will not discuss further. I have many things to discuss. So this is wrong integration. Okay. Next, this three what I have given here, use of d. This is first example. Example A, 1 over. B you follow. This is very important. B is what? Criterion of equilibrium. Criterion of equilibrium. You are using frequently this equilibrium. What is the criterion of equilibrium? You consider this. dgpt is 0. This you know very well. You know dgpt. Now I'm giving you. My question is, if the state is under equilibrium, see, minimum. I'll show you. This is the minimum equilibrium. I will give the sketch, full sketch later. Short. If this is equilibrium, how dg means change after all. Small change, infinitesimal small change. At the equilibrium, if you change little bit, infinitesimally small though, small even, very small. What it goes? This is the free energy minimum. Minimum, G minimum. Then if you make a change, dg means change. dg tends to 0 though, but change, not 0. Change, not it is tending to 0 only. So this point is the dg set. This point to this point increase at any item because it's the minimum. Next point is greater. Even not this side only, this side also greater. That's why it is minimum. So any change should be greater than 0. First question is, why there should be any change after all? dg is a change, kind of change at equilibrium. How can you think of change? change in anything, change in free energy, change in number of moles, it is stopped. Equilibrium state. How can we, even if we admit that okay, that is a change, then it will increase. This is the main thing. Let me explain this actually in tidy way. After the, this is my confusion. This is my confusion. That's why I have to, oh, by the way, first you write, please. Please write here, please. By all means, write this. This is actually my personal, my individual opinion. So you should write this. I forgot. Individualistic opinion of the instructor. Of the instructor. Instructor. This is my opinion. Individual opinion. This is my understanding of this. Why this subject has been difficult. Anyway, now follow this. After the equilibrium, my question is this: after the equilibrium is attained, after the equilibrium is attained, let me write this. There can't be any more change. Any more change, or you may write, if it is a reaction, progress of reaction, progress of reaction, progress of reaction. Then then how is dg relevant at equilibrium? No change. Equilibrium means no change. Any furthermore, no change. But after all changes, it has come to equilibrium. Through changes, changes comes to equilibrium, and there is should not be any more change. Okay, very good. So this is, even so, even if we consider now, so first of all, it is how it is relevant. Even if one considers, if one considers an infinitesimally small infinitesimally small change change dn dn change, dn moles change past the equilibrium state, past the equilibrium state, past the equilibrium state, the corresponding dg will be, the corresponding dg will be positive, positive, positive. Any change? Positive, as so is should be positive, not zero. What is said? Zero, zero, not zero. You underline this individualistic opinion of the instructor. Okay, Dg will be positive, not 0. Okay, not 0 as is shown below. As is shown below in figure 1. Okay, in figure 1. In the light of the reactions, in the okay, quick little faster, in the light of the sorry, I'm very sorry, in the light of the reaction A plus 2B goes to 3C, our popular example which we have already used. So let me draw this figure. This figure actually I am drawing now correctly, fully. This. Happy? This is your actually G prime PT, right? G prime PT. This is a constant pressure, constant temperature, process, and this is your minimum coming. So this is your minima. Call this point E. Just point, state E. This is E point. Okay, and what are the A plus 2B this side, 3C other side, NC moles. How many? This side is 0, that side is 3, and N, if you write in terms of N, which is 1/3 NC, 1/3 NC, N is actually neither Na nor Nb nor Nc. N is 1/3 NC is what? It will be 0 here and it will be 1. Not bad. So this. The question is, okay, so let us see. It's okay. So if the system is the equilibrium state at the minimum of GPPT versus N plot. You know this? This is equilibrium. If the now since the G change is mentioned, so we'll change this. First of all, we have wonder how that should be changed because it is equilibrium. Even so, if it is considered there is a change, so that let us see. Now, if the system is considered to move, shall I write? I'm giving star here. Star. It is better I write this side. It will be better for me. If the system is considered to move, considered to move from E to E prime, move from E to E prime, very close to this dn moles distance. I cannot show here, but I am showing here just for your benefit. This is my E prime. I have to show finite change, but it is infinitesimally change. You understand that E. This is E. This is E prime. So here to here to E prime. I'm mentioning this E and E prime are dn moles apart. Are dn moles apart. means infinitesimal change. dg is infinitesimal change, so is we have considered infinitesimal change. Or apart, the corresponding free energy change is dg. The corresponding free energy change is dg. So dn, so dg change. This dg we have taken under constant pressure, constant temperature, dg dg is dg. So from figure 1 we see from figure 1 we see dg is we see dg is actually is here dg prime, the way I have written. Not only that, dg prime pt more completely defined, dg prime is dg prime pt. Or dg is what we see, what dg is what dg change between this and this is positive, is positive, is positive. That is, since see here from the diagram, g e prime, g of e prime here, sorry, g of e prime here, g of e here is up, going up. So g that's greater. So g is greater than, so this is the problem. So this is the problem. That means we don't understand this. What does it mean? We do not mean, or I do not understand what is this criterion. This is we derived. We derived from where? The second law, original second law, dx universe greater than 0. Then in terms of free energy, we got this. Less than 0 for spontaneous, equal to 0 for equilibrium, and greater than 0 for impossible. And not only these, other state properties, Helmholtz free energy, A, enthalpy, internal energy, etc. So they consider this. So we found this, but we do not know how it is equilibrium. How does it represent equilibrium? Now the answer. Now I will give you the answer, and most of which you know. Shall I remove this? I remove this. These are not required. These are not required. These are actually already. So I am giving you the answer. So answers I am giving. So this. So this is the answer to this puzzle. Continue from this. The answer. Remove this. This you remove. In fact, we can remove many things. So this will be, with this answer. This second this problem will be over. This is what? This is A. This is B. Remember, this is a B, problem B. I have removed this. It was B. It is A already over. B will be soon over. Then still another C. I'll take up. So B, C. C. Three examples. Okay. Use of D. 3 examples I'm giving. I'm giving 3 examples. So A. This was B. The confusion about D. Why it is difficult to understand thermodynamics. See what is the the answer to the puzzle. This is puzzling. The answer to this puzzle is we have already discussed. Is what we know, what we already know. What we already know. Let us start. What you already know. You easily follow this now. The difficulty is where is this? The second law. Second law for equilibrium. Condition for equilibrium. This is the main question. This is the main question, right? This for equilibrium. Second law is what? You tell me. ds universe. Acha, I remove this first thing, and I just write about this. dgpt is 0 is our troublesome relation. Okay, this actually is our okay. Uh, is what we cannot understand. Okay, is our okay. This is actually our bottleneck. You may call it okay a pitfall of our understanding. This dgpt is 0. This is the questions. The criterion of equilibrium. You save this here. This is the sole point to us. This dgpt is 0. We cannot understand this how it is equilibrium. So far I have shown everything. Now I am giving the answer. The puzzle. It's a puzzling. This is puzzling to us. So this means the second law of equilibrium is what? Right? Tell me. Start original. Second law. ds universe, or alternatively you write always isolated system. Same. uv constant u constant v. Constant u constant v is greater than 0. Oh, I am very sorry. For equilibrium I am considering not spontaneity or impossibility. No, only one. ds universe. Then this leads to what? Remember, this was proved actually in the class. This was proved, okay, because this is in the universe. And what is the, let me write, dgpt or is actually dg prime pt variously written is 0. This is actually why. What is the difference between this? This is okay universal criterion, but the problem is it is about universe, system plus surrounding, but this is about system alone. So that's the advantage. That's why you often use in our problem free energy, gives free energy. Anyway, that is already discussed. So dgpt is dg prime pt is 0. Okay, from which you get, now see, dg prime, if it is 0, dg prime pt by dn is 0. dn is a positive quantity. dn is a non-zero dn change in non-zero. So it is, if it is 0, it is 0. This gives you one quick nice comment, very popular comment. What is this? G prime pt. This is about all equilibrium. For underline for equilibrium. G prime pt is minimum. Is minimum at equilibrium. This one very common statement. Still another is what? Tell me next. This is one. Another is, in fact, this concept you use in I'm digressing much. This concept you use in, what is this called? Computational thermodynamics. Computational thermodynamics you use this. That find G prime pt for okay for actually range of compositions. For the whole range of compositions, see find which composition this is minimum. That is the equilibrium composition. This software, okay, FactSet, perhaps use this. Okay, you can use yourself. I used actually solver, another one smaller version though, but smaller software, but give the same very easily. So this is one very popular. Why you say, when you say minimum, means this is the minimum. This is versus n. G versus n, so derivative is 0. Next is what? This leads to delta G. Now see. So here where dg, suddenly we enter into delta G, interest without integrating. Without integrating delta. Very interesting. So if you put delta, you have no difficult. Anyway, follow. Delta G is 0. Why? Since dg prime pt, this derivation, you go back and see. I have shown you everything. So delta G dn. What is delta G? Tell me. 3 Gc bar minus Ga bar, product minus reactant, as you know. Oh, where? DGPT is dn, okay. Where delta G is? Very sorry. DGPT is dn, hence, and this is delta G. Where delta G is what? Where where delta G, oh sorry sir, I'm writing, where delta G is, where delta G is 3 Gc bar minus Ga bar, okay. This is the delta G, partial molar free energy at this state, at this state. Partial molar free energy means, related to activity and composition, and activity coefficient, etc. For gases, partial pressure, activity. So these are composition, total pressure, all this business. The total pressure is given here. So I don't want to. So where delta G is Tc. So this is the one. This is your. This refers to. So clear. This refers to. Note this. This refers to a single state. To a single state. The equilibrium state. That is our state E. This is, see, this delta is a product minus reactant. So delta, from we are no longer with dg. Okay, delta very easy. Delta very useful. At this state, there is a delta, not two states, one state, but still delta possible. This I discussed previously, so I should not repeat all these things. So delta this. So this is the meaning of this. This is the meaning of this. Leads to this. This leads to this. Delta G is 0. That they have the same free energy. 3 Gc have the same free energy as Ga bar plus 2 Gb bar. Hence, the difference is delta G is 0, and that is the outcome from this. So this is this over. This is over. Quickly. This B is over. C. Let us start C. See, 3 examples I told you. So 3 examples I told you. See, so let us start. This is removed. This is okay. So what is our discussion? Use of D. Confusion. And why students get okay, stumbling block. Acha, we often write. We often write. Quickly go it on. We often write what? Right? The mechanical work dW is PdV. dW is PdV, which is correct for the reversible process. See, I am dealing with again D. Use of D is correct for the reversible process. Okay. Not for an irreversible process. Unless constant P. Unless under constant P. For example, this is for I'm explaining, if it is say adiabatic or isothermal process, this is not true for irreversible. This is true for reversible. If it is constant pressure, this will be represented. This will represent both reversible and irreversible. And not only constant pressure, I have not written here constant volume. constant volume I have not written here. That is also true under constant pressure or constant volume, because when constant volume there is no change, no work done itself. So both same. Reversible is irreversible. But if it is a other than constant pressure, like adiabatic process or isothermal process, dW is PdV for exclusively for reversible. For irreversible, it is not. What it will be? Start. The correct relation for dW mechanical, mechanical means PV type work. PV type work. dW mechanical is dW mechanical. Okay. dW mechanical is what? Mechanical is dW mechanical is P external. Mechanical is P external dV. This is very important. This is the definition of mechanical work. P external dV, where external, P external, right? External refers to surroundings. Or external refers to the surrounding. Please you know. Now, given this, you remove all these things, no longer required. Quickly. Move on. So what you have? And this gives for the following expansion works is for the following expansion work with P as the system pressure. With P as the system pressure. This I discussed in the class, but I want to actually add some points here, so that's why I have taken up this. dW mechanical will get this. P as the system pressure, dW mechanical, in short mechanical. P external will be what? P external will be for reversible. Shall I write here reversible? That I have omitted. Reversible I am considering. dW mechanical. This is the definition for reversible and irreversible. For reversible, what change? P external will be nothing but system pressure is P, and dP is the infinitesimal small driving force is dP. P minus dP will be the pressure. P external will be system pressure P minus dP for expansion. I have written as expansion. If it is compression, it will be P. If it will be compression, then it will be P plus dP. Since expansion, so there will be outside pressure will be slightly less, so expansion system pressure is greater. So dB is PdB. This is how we get the famous PdB. But it is what? For reversible process under this, okay? What is this? For reversible, and if I ask me isothermal process or what is that called? Adiabatic process. Okay. So, but anyway, you see this PdB is. I will show you here. This is PdB. So what you are going to write here is PdB note dP, dB always tends to 0. Anything, any dx, dy, dz, any d, dh, dg, ds, du, all tends to 0. Okay, infinitesimally small. So this note. Now, dw mechanical irreversible is what? Tell me. This is infinitesimal. Acha, you write here. I should write there, na? Acha, acha, ठीक है, okay. In the context. Okay, very good. Very good. It will not take much time. dw irreversible is p minus. Tell me. Driving force is finite. Delta p. Not dp anymore. Delta p is a finite quantity. is what? Is not anymore pdv. This applies to adiabatic and isothermal. As I have said, constant pressure and constant volume. Constant volume, no work, so no change. And constant pressure, no change also. This I discussed in the class. Is not is not pdv. Note. Oh, I'm sorry. I'm very sorry. Note. Here. Timing force is note dp tends to 0. I'm very sorry. Very sorry. Yeah. P minus dp tends to 0. But delta p, yeah, together. But delta p, which is integration of dp, is any finite quantity. Is any finite quantity, big or small. Like it can be 0.01, it can be 100. It can be 0.00001, it can be 1 million. So any value, any finite value. But this is actually exceptional. This is unique. dp tends to 0. Okay. So anyway, this is okay. Now I write here note. Here note p minus delta p likewise can be any actually this part unnecessary. Okay, let us move on. So in this context, so this is first of all, right here, applicable for isothermal and adiabatic expansion of ideal gas. So for compressor it will be plus p plus dp. It is p plus delta p. Okay, it's not pdp. Okay, but I am giving you. So p minus delta p. You see, delta p can be any finite value. It can be any value, any finite less than p. So if p is 1 atmosphere, delta p can be 0.5, 0.6, 0.7, can be even 1. If it is 1, same as p. When it is same as p, what is this? Delta p, the driving force. Shall I write the driving force? Okay. I write there. Driving force, a moment. If it is driving force, that difference, driving force can be same as the p, then what is the value? P is delta p is same as p itself, that is 0. 0, when it is 0, it is known as, already told, it is against p external is 0, means against 0 pressure, against vacuum. That is called free expansion. This is something in passing I actually mentioned. Don't worry, I have already given whatever required. Here, in this context, in this context, another faulty notion, another faulty notion is that a differential change, a differential D, differential means D, differential change is applicable exclusively to a reversible process. Means when you consider any change du, dh, you think it is a reversible process. So any the moment there is a d, we think reversible process. But okay, but it can be for irreversible process. This is mentioned here. Is possible, but a differential change. Differential change means infinitesimally small change. D is infinitesimally small, which tends to zero. Differential, but a differential change is possible with an irreversible process too. With an irreversible process too. Excuse me, with irreversible process too. Okay. For example, can I remove this today? This one. Process 2. Just go up there. Sorry for the interruption. Sorry for the interruption. For example, for example, for isothermal expansion of an ideal gas, for isothermal of an ideal gas, starting from the same initial state, by the same initial state, five minutes, 5, 6 maximum. From the same initial state, the system can be made to reach this system can be made to reach can be made to reach the same final state, that is in both cases reversible process and irreversible process, same initial, same final, and differential change, both possible. This we want to show that D can be applicable for irreversible also, but how? That is, let us follow this. And made to reach the same final state, these two states being dV volume apart. Since it is expansion, the two states, we start with volume V1, V1 plus dV, both ways. So dV change. Reversibly, irreversible. Reversible isothermal, irreversible isothermal. The two states being dV volume apart. The two states being dV volume apart. dV volume apart in either case. In either case means in reversible and irreversible. In either case, dV. So dV means differential change. I have given to the irreversible also. But how? Either case. Only now see. Only in the case of, follow this. In the case of reversible process, reversible process, reversible process. In the case of reversible, the external pressure is that you know from this previous lecture here. The external here. Reversible, irreversible. The external pressure external pressure is actually surrounding. This is actually about surrounding. External pressure. External surrounding, I have noted here surrounding. External pressure is P1 minus dP, where dP, P1 is the right. P1 is the initial pressure of the system. Initial system pressure. This is the initial pressure of the system. Pressure of the system. You know dP. P1 is the system pressure, initial pressure of system. P1 is the system pressure, and the driving force is driving force is how much? Driving force dP, and the driving force is infinitesimally small. Reversible, infinitesimally small. The definition of reversible, infinitesimally small is infinitesimally right. Has come in line. Okay. Is infinitesimally small. What is that value? dP. Okay, this is dP. And in the case of remove this. And in the case of let us see how will we arrive at the same volume change dV with the help of a finite driving force. That is interesting. And in the case of irreversible process, the external pressure is external pressure is P1 minus dP is pressure is, I am very sorry, P1 was not dP anymore, it will be delta P. It will be delta P. Means finite change. Where delta P, the driving force is a finite quantity, is a finite value, delta P. P1 minus delta P. And an arrestor is required. And an arrestor is to be provided this is the extra thing for irreversible, extra thing. Same, it will stop when the volume change will be dV. An arrestor is to be provided in the is required in the cylinder piston arrangement to forcibly stop the rising piston. The rising piston rises and stop it. Forcibly rising piston at the same final volume. At the same final volume. What is the final volume? Tell me. V1 is the initial volume. Have I written somewhere? V1 is the initial volume. I wrote somewhere. Okay, V1 is the initial volume. I am writing now. At the same final volume, what is the final volume? Sorry, now I am writing V1 plus dV. V1 plus dV, where V1 being the initial volume. Initial volume, as in the to the same final volume as in the reversible process. So with this we have completed this first issue. The second issue, next day, second, third, fourth, next class, reversible process, presence of constants in thermodynamic relations, and last is concept of equilibrium. This will be discussed in the next class. Thank you very much for your cooperation and for your attention and for your interest, for your devotion and for your uh, for your sincerity and all these things. Okay, thank you very much. So we call it a day today. We'll meet you next class. Bye. Okay, until then, bye. See you later. Okay.